Welcome to Advanced Strength of Materials. I'll be covering the summary of elasticity equations again, and I'm doing that on purpose to drive home the point of what the equations really are. And then we're going to apply it to plane stress and plane strain. I want to explain what that means in the context of elasticity, which becomes quite important. And these are very nice assumptions that can be used to simplify models. So the three governing equations are shown here. You can see the three stress fields or the three equations of elasticity that was derived using Newton's law. We have then the six strain deflection relationships, which relate the strains to the deflections. And then we have the six stress strain relationships, which relate the stress to the strains. So as you can see, everything's interconnected here. This is matrix notation, so there's clearly six equations here. It's just that I have it in matrix notation. But in general, if you notice, if I took the strains here, plugged it into this equation, then the stresses will be in terms of deflections. And when I plug all that into these three equations, then everything becomes in terms of deflections only. And so you have to solve for deflections, and that's not an easy thing to do. All I'm doing it for very, very simple problems so you can see how that works. Although for more complicated problems, it is very hard to do, which is fine. Just showing you how this works. Excellent. So, boundary conditions, we can specify tractions or displacements, but not both at the same location. We discussed that. So I can apply tractions here, I can apply displacements here, but I cannot put displacements and tractions at the same time. And what are tractions? Are loadings that you can apply on the surface of the body of the material. So what are the different interrelationships? How everything connects with each other in this diagram is that I have external loads applied. I can connect that to the stresses that are acting inside of the body, which react to external loads, because stresses are internal load quantities that are per unit area. And then the stresses are connected to the strains connected to the constitutive law, and the strains are connected to the deflections through the strain deflection relationship. And so here, what we're really looking for is equilibrium here. And we cover that. That equation, I'll just write one so you know what I'm talking about. That'll be the partial sigma xx respect to x plus partial sigma xy respect to y, partial of sigma xz respect to z, plus the body force in the x direction equals 0. And there's three of them like that. And then here, what you're looking at is how the strains there's six of them. There's this by 1, 6 by 6. And there's your 1 over e, your modulus. And that's 6 by 6. Etc. And then 6 by 1. So here you have it. You're multiplying these things together. And that relates the stresses to strains. And then what relates strains to deflections is your strain deflection relationships. And there's 6 of them. So there you have it. I'm kind of showing you all these equations here, but in this diagram, there's 3 equations here, there's 6 here, and there's 6 here. And what are the unknowns? U, V, and W, that's 3. Sigma XX, etc., 6, and strains 6. So that's 15. So 6 equations, 6 equations, 3 equations, that's 15, and then 15 unknowns. So you have enough to solve there. So let's look at the 3D nature of stress, right? So um, there are special cases when you have stress applied to a system. So you may have a body of material that's subjected to a lot of different loads, right? So on the left side, you can see that I have loads applied in different locations. But this body of material, if I took a little cube and looked at it, that body of material, the stress field is well described by these 6 components of stress. But there's no real way to simplify this model into anything useful. You can only model as 3D. This can be then specialized and looked at later on by looking at dimensional simplifications. I'll go into that in a second. So, but for a 3D body of material, the constitutive law is given by the equation that you see here, which I've been writing over and over in a simple way. I think I was doing this 1 over E, 1 over E. So that's exactly what you see here. I just put the 1 over E here. But it's the same thing that I've been typing all along. So like here you saw it. I was typing it here. That is right here, this equation. And how you calculate this relationship? You calculate that relationship using experiments. That's how you determine the Poisson ratio and the modulus. You go, you have a round bar, right? You load it up, and then you know what the initial deflection is. So I can calculate the strain, and I can calculate the stress, and I can plot it. And that slope is the modulus, and the Poisson ratio is easily calculable by putting strain gauge this way. And that strain gauge is going to be the minus nu of epsilon xx, and I have this strain gauge. That gives me this number, that gives me this number, and from those 2 numbers I can calculate nu. Right? So that's how you do it in experiments, fully done, fully doable. But what is plane stress? It's a simplification from the 3D state of stress. So this is true always, but plane stress is a condition. Say you have a thin plate, right? So that's a thin plate here that you see, a very thin plate. So this plate is very thin, right? H, it's not close, not exactly 0, but it's close to 0. So it's fairly thin. And all the loads you applied are in the plane that you see there. So they're all in the XY plane. You could have an out of plane loading condition and still trace plane stress, no problem. Just showing you what I'm doing here. Okay, so it turns out that in this assumption, what we're saying is that through the thickness stresses are 0. So any stress corresponding to sigma ZZ is 0, and I'll explain why that is the case. Okay, so in plane stress, what we're saying is if the body is fairly thin, I can make this assumption. I can make that assumption. Why is that? So let's think about that. So let's look at this phase, that phase. So in that phase, if I don't have loads applied to this surface, right? And let's assume that this top surface is a z equals plus h, and at this surface, z equals minus h. So let's examine using Cauchy's relationship what is going on. Okay, let's look at that carefully so we can understand what is going on there. So tractions equals stress times the normal. But I want to examine that face here. That normal is 0, 0, 1. And in that surface, I have no tractions, nothing. So that's tractions equals 0, 0, 0. So therefore, I have 0, 0, 0 equals, and I'll type it here, symmetric. We know the stress tensor is symmetric times the vector 0, 0, 1. When I do this multiplication, you can quickly see that from here, sigma xz equals sigma yz equals sigma zz equals 0 at z equals plus h. I can repeat this multiplication. I can repeat that multiplication with the surface, but on this side now. And that surface has a normal n that's 0, 0, minus 1. When you do and repeat the process, you get the exact same thing. You get that these are also equals 0 at z equals minus h. But the plate is already very thin. And if you have, a very thin plate, if I have a very thin plate, then stresses cannot quite develop much because is 0 here, all these 3, is 0 here, all these 3. So in between is going to be close to 0 because there's no way it can develop a lot of stress given that's already very thin. Okay, so that's what the plane stress assumption is. So, so that's sort of what I'm talking about there. Um, another picture here in 3D. You can see here I took a cube out, and the cube out, what we're saying is that that stress, the shear stresses, are at that face there, right? So that tangential stress to that surface is 0, right? Because it cannot really develop through a thickness. Another plane stress example. So this is a thin plate. Another one could be the I-beam. That wall here, this wall is very thin. You can see there, that thickness there, see, is very thin. So if I look at that plane, in this case, you can see that the stresses in the z direction, which is perpendicular to this surface, any of the components of stress in that direction are also very close to 0 for very thin web there. So in my book, I explain what that implies. What it implies is that these stress states here that have to do with the z direction of 0. That's what it implies. And right now, I'm ignoring. I'm not ignoring anything. I'm just saying that stress states are close to 0 for those components. So these are much lower in magnitude than this one. That's what this means. Much lower. Much lower is what I use in my book. Okay. So when that is the case, I can examine the constitutive law carefully. You can see here that all I have to do is set this equal to 0 for the top 3 rows. So here what I'm doing. So you can see what I'm doing here. Let me erase all this so it's not cluttered and you understand what I did there. What I did there, I focused on the first 3 equations. So this one's right here. This is 0 because we said that for thin plates, that is the case. So I'm focusing on those first three equations, not the last three. I'll look at that in a second, but as you know, the thread thickness is 0 anyway. So, and that's easy. That's just saying that gamma xy equals G sigma xy divided by G, the shear modulus. Um, since these ones are 0, these shear strengths are 0. So I'm not going to look at those. I can look at the last equation easily, equation number 4. But I'm going to look at equation 1, 2, and 3. And that's what I did there. That's why everything looks so simplified here in this right here. I just took the first three equations, extracted them out. When you multiply, since sigma is z is close to 0, I can then multiply the first row times the column, second row times the column, and third row times the column. And when you see that z does not show up anywhere, that's the only thing that happens. No problem. Okay, so that's what you see there. Because of the Poisson effect, it turns out that although the stress in the z direction is close to 0, you do get a strain associated with the z direction. And that's that. That strain is going to happen. So if I have any loading condition within the xy plane, you will have a strain in the z direction. So let's look at this example. If I apply loads that compress this material, say, I do expect the thickness of this plate to change. So let's look at what that means, right? So let's try to understand physically what are we talking about there. I want to make sure that's clear. So say I apply a load in the plane that you see there, this XY plane, right? If I apply a load this way to compress it, say, this thickness is going to increase in size. But that thickness is directly related to epsilon zz, right? Partial W with respect to z. So clearly, that strain is going to matter. Now let's look at the condition for plane strain. So what is plane strain? You know, I show on the top left an image from the third edition of Ugrol and Fenster Advanced Strength and Applied Elasticity book from 1995. And on the top left, what I'm showing is a long prismatic member that's fixed at these surfaces, this one and this one. So there's a lateral load applied in the XY plane. So say you have a pressure load applied on this cylinder. So let me just take this here to kind of illustrate. So this is the pressure vessel. And I'm applying pressure there. Okay. All cross section, if that's the case, are going to experience the same deformation. Every single cross section. That cross section is going to experience that. That cross section will experience that. That cross section will experience that. If that is the case, then epsilon zz, which is the strain in this direction, will be 0. There'll be no shear strains that have to do with z, will be 0. Again, that's only if I take this tube that's pressurized and is held fixed between these two rigid plates. So that is called a plane strain assumption, a situation where you have a very long member usually will act in this way, right? So that's when you will see that situation. I encountered this quite a bit, and that's a plane strain can be a very good assumption in those cases. So what does that mean from the constitutive law standpoint? It means that these strains here are close to 0 relative to, and this is from my book directly. And when this is true, it tends to be true when you have very long structures where the deformation is not expected to change along the z direction. And this is the example we talked about, right? So this example right here is fixed. So this length is not changing. And the deflection I think I'm gonna give here is the same as the ones here. So if I invert Hooke's law, and what I mean with inverting Hooke's law, if I invert Hooke's law here, this one here, invert it to get in terms of stress, what you get is that since this is close, this is the one that we said was 0, you get this equation here. You get that the stress now shows up. This stress is going to show up. Sigma ZZ will show up due to that assumption. That makes sense because I'm fixing the plate in the Z direction. So if I'm applying a pressure to the structure, something will get generated also in this direction. This strain also is the only one that shows up. The other ones are 0. And that normal stress shows up as well, right? So this is a book compares plane stress to plane strain, which is very useful. And that comparison shows what stresses are 0 for what condition. So here, what you can see is for plane stress is exactly what we said, that in the Z direction, thickness is very small. So H is close to 0. And therefore, sigma ZZ, sigma XZ, sigma YZ are 0. And then the other stresses are non-zero, okay? Strains, on the other hand, because these are 0, this has to be 0 as a consequence. And you may think epsilon ZZ is not is 0, but it's not because we said that shows up. So in reality, for plane stress, you have 7 values are non-zero. You have these 3 and then these 4. So, so we don't have a lot of clutter. I'll delete this and then kind of move to plane strain next because it's like a summary slide. So what is going on the right-hand side is I may have is a very long structure. But the cross-section of each of these here will be the same. The deflections there in that cross-section will be the same, which means that the strain epsilon ZZ, gamma XZ, and gamma YZ will be 0. As a consequence, these two have to be 0 because they're related through the shear modulus. And then these are non-zero. And then you get these stresses that show up, but you also get this one that's related to the constraint of epsilon ZZ. And that concludes the explanation of plane stress versus plane strain, which is very, very convenient because if you can derive those, if you can make that assumption, they can really simplify the modeling quite a bit. And it's used in industry quite a bit also. With that said, I'll see you until next.